Well, when you threw me into the black hole and watch how I'm approaching the horizon, you'll see that for me time slows down. And you'll get tired of watching me fall in, you'll go have some tea, then eventually retire, write a book about how you did it. And I still won't make it there from your point of view.
Physicists now have a saying. You can watch endlessly how water flows, how fire burns, and how someone falls into a black hole.
This, literally, can last infinitely long.
This is Azatosium, and we are together again with Woman 1, a physicist.
And with me, Woman 2, an astronomer. We decided to talk about Einstein's theory of relativity. Hello, everyone. Hello, Einstein. And we thank him for this topic. Now we have the theory of relativity, which many people view differently.
Well, first of all, there are two of them.
Listen, it turns into a kind of tautology. People have different attitudes toward the theory of relativity.
Listen, you can relate to it however you want, accept it or reject it. But our concepts are tested by daily practice and experiments. The theory of relativity is something built into science. Let's not be hypocritical. There are questions about it, and we'll discuss them. But let's start with the main point. It is systematically integrated into the modern picture of the world.
Wait, let me tell you a completely different story. The theory of relativity isn't built in, and even school physics doesn't always match our everyday experience. Look, before Newton, Aristotle claimed that uniform linear motion was only possible if you kept pushing something. And our experience seems to agree. A car moves at constant speed only when the engine is on and fuel is being consumed. Let go of a cart and it stops. This is our daily experience, the way our bodies and brains are tuned. Then Galileo appears with his principle of relativity, and Newton completes the picture by saying, no, if no force acts on a body, it will move uniformly and straight forever. And to change motion, you need to apply a force. This contradicts our everyday experience, but that's what we're taught in school. Newton was right, and his laws are the foundation. Engineers use them, and this becomes our second, school-based experience. Eventually, all engineers know Newtonian physics is reliable. Devices, machines, vehicles built on his equations work. That's proven experience. Then Einstein comes along and says, it's not like that at all. And suddenly there's a kind of cacophony, even a certain idiosyncrasy. But we'll come back to that. Because even the one who stayed on Earth isn't in a vacuum, he's in a gravitational field, where time also flows differently. And we'll come back to that as well.
All right. This is a wonderful story that shows our concepts work for us as long as they describe our experience. But notice, the most remarkable part of your story is the time before Galileo, starting with antiquity. Back then, there wasn't even the idea that the physical world could be described quantitatively. That is truly surprising. People were interested in geometry, but they didn't think that nature itself was governed by quantitative relationships.
And what about Ptolemy? The motion of the stars, the motion of the planets.
Here's the point. All the mechanics back then was still Aristotelian, a qualitative understanding and a deliberate refusal to measure. Galileo started measuring, while Aristotle didn't want to, because he believed the physical world couldn't provide quantitative data, that it couldn't be described numerically. But once Galileo began measuring, he did something remarkable with the power of thought. He mentally removed air resistance. He changed the angle of the inclined plane. On the level of thought experiments, he asked, what if there were no friction, no resistance at all? And then it turned out that what we perceive as the natural state, the absence of external influences, is in fact the presence of an influence, the resistance of the medium, the resistance of the air we are used to. We simply need to realize that part of what seems self-evident is also a factor of influence that shapes our experience. That's how I understand it for myself.
So Galileo was no longer relying only on pure experience. He started imagining what the experience would be like if it were even more ideal.
Yes, this was a very strong side of Galileo. He constantly did such things. He was the first in this sense, a true forefather of the modern scientific view of the world. He conducted thought experiments that cleared a situation of factors that couldn't be removed in reality. For example,
Exactly. Planets move with almost no resistance.
So it began, practically without resistance. And when you talk about why two black holes still come together, how they lose angular momentum, this is where it comes to mind. They move at such speeds that they interact with the surrounding medium, scattering it, and in doing so, they transfer angular momentum, and so on.
Well, this was already a higher level. Isaac Newton was helped by the fact that he already knew about planetary motion. For Galileo, these were only the first steps, the telescope, and so on. By the time of Newton, almost a century had passed, and during those 100 years, astronomers had studied the details of planetary motion very well, the laws of Kepler.
So, Kepler came first. Newton was born about 12 years after Kepler's death, 3 generations from Galileo to Newton. For Newton, there was already an experimental fact. Planets move in ellipses with the sun at a focus. The second and third laws of Kepler hold. The second law relates to speed, and the third to periods and distances. Logically, they are not connected. Kepler even searched for a fourth or fifth law, but without success. And then suddenly Newton says, "Dear friends, I propose not to limit ourselves to these empirical facts. They are, of course, good, and we will consider them correct. But I will replace them with a devised equation, 2 laws of motion, and the law of universal gravitation. From these, I will mathematically derive everything else." Everyone was satisfied.
By Newton's time, mathematics was already a reliable foundation for the natural sciences. Yes, it was clear that without it, any claims would remain unstable.
This is a somewhat tricky question, and it's a bit hard to answer right now, but here's why. Galileo said that the book of nature is written in the language of mathematics. The full quote is longer, and Galileo specialists might correct me because it has additional meanings, but the main sense is not contradicted. Newton created the physical picture of the world and at the same time developed differential and integral calculus, which was necessary to describe it. Solving second-order differential equations allowed describing motion. The ideal application of this system is where there is almost no resistance in space. There, planets move very accurately until anomalies appear. For example, an anomaly in Uranus' motion was explained using Newton's laws, which further increased their authority. It was hypothesized that the cause was an unseen planet. Using Newton's laws, its position was predicted with decent accuracy. Adams was slightly less precise, Leverrier slightly better. 15 years later, observation accuracy improved, revealing another planet. Another example is Mercury. Its orbit was slightly anomalous. The ellipse itself slowly rotated by 43 arcseconds per century.
This is how well astronomers can measure.
You know, it's amazing. It's simply astonishing to realize this happening with the ellipse while sitting on the moving Earth and looking at the sky at these barely visible points. It absolutely astonishes me, especially Mercury, which is almost invisible because it is so close to the Sun.
Listen, did you know that the ellipse of Mercury's orbit actually moves through space much faster? Its axis shifts by about 550 seconds per century. You have to subtract the effects that are understood, the gravitational pull of Venus, Jupiter, Earth, and so on, and a tiny fraction remains, less than 10% of this motion. And they still weren't satisfied until they found an explanation.
It's amazing, it's true. I keep forgetting about this. Thank you for reminding me. In fact, the discrepancy was roughly 10 times larger, and it was initially explained using Newton's laws, the influence of other planets. They subtracted everything they could, and a tiny fraction remained, naturally leading to the hypothesis of another unseen planet. This planet was named Vulcan. Why? Because, in modern terms, it's a hot super-Earth. There are many such planets now, 5 times the mass of Earth, orbiting close to their star, sometimes completing an orbit in just one day. We see many star systems with such planets. So, it would have been reasonable to assume such a planet existed. Mercury moved incorrectly, but the real explanation came only from Einstein. We'll return to general relativity later. When Einstein developed his theory and applied the complex formulas, he obtained a value of 42.99 arcseconds per century, while observations showed about 43. According to him, He was overjoyed for a day and a half. It's hard to imagine how a person must have felt after 7 years of building an extremely complex system, making mistakes, taking wrong paths, and finally achieving such a result.
The main thing is that he explained what no one else could at the time, and it was unclear why this theory might be needed, except for Mercury's motion.
Do we want to jump straight to general relativity, or should we start with special relativity? Let's just clarify. 1905 is about special relativity. It concerns how electrodynamic phenomena, that is, the propagation of light, are perceived by different moving observers. In 1905, there were many ideas, some still in the air. Einstein formulated the physical principles, then mathematics was added, a group understanding emerged, and Minkowski space was introduced, all in modern terms. After that, Einstein spent 7 to 8 years focused on one problem: how to generalize this in the presence of gravitational fields. This led to the theory of gravity, which explained why Mercury is attracted to the Sun not exactly according to Newton and therefore moves differently. For historical reasons, this theory is called general relativity.
Is this the correct name?
Yes, well, that's basically the name. It's the modern theory of gravity, which is constantly discussed today. We keep jumping ahead, but what can you do? You provoke me. In fact, it's always being discussed for a reason, whether modifications are needed, whether it holds true at large distances, in strong gravitational fields, or when quantum effects are relevant. That's a separate story. We know it's not absolute, so there are limits where it can't be applied. The most interesting part is the singularities of black holes. They arise because the equations of general relativity break down. There's also the question of whether adjustments are needed on other scales, at large distances. This relates to dark matter. It's a complex and interesting question that we keep thinking about. But for now, in practice, this theory is our best theory of gravity.
At that time, were there alternatives to the theory of relativity? Were there versions that also predicted the behavior of light fairly well for different observers?
You're talking about 1905, about the special theory of relativity? The question young Einstein asked was, what would a runner see if they ran while holding a mirror in front of them? Would they see their reflection if they ran at the speed of light? The answer turned out to be very elegant. Such a runner cannot exist, because you cannot attach a reference frame to light. This question was about how to transform electrodynamic phenomena, the electric and magnetic effects that were already well understood for different moving observers. Previously, this could be done in different ways, assuming there was a single medium, the ether, in which light propagates, and where the speed of light is defined. This seemed natural because we are used to waves always propagating through a medium, for example, sound through air. At that time, it was necessary to introduce a large number of corrective factors that would specify, if I move relative to the ether, I must apply certain mathematics in a certain way.
Yes, there were such alternatives, right?
Yes, such alternatives existed. In fact, Lorentz invented what is now an integral part of special relativity, the Lorentz transformation. It's a way to convert measurements from one moving observer to another, but Lorentz developed them earlier. They were simply applied to other problems. Einstein adopted them, presenting it as a trick which actually reflects the natural state of things. He proclaimed the principle of no ether and the equality of all observers. In special relativity, there is no absolute Newtonian space. One observer's perspective cannot be preferred over another's. Observers may perceive the same events differently, but our conclusions about the behavior of a physical system must be consistent, despite differences in details. Another crucial point: special relativity begins by proclaiming the constancy of the speed of light, which contradicts our everyday experience. If you measure the speed of light while sitting still, you get about 299,792,458 kilometers per second. If I move toward the light beam at half the speed of light, I still measure the same speed. Even if an operator moves in the opposite direction, they measure the same value. This defies our intuitive experience of speeds and produces other effects we do not notice in daily life. When accounted for, however, everything becomes internally consistent.
Were there direct experiments where one person was flying, another staying still, and they both measured the speed of the same light beam to see if it was the same?
Look, there were experiments done by Alexandrov at the accelerator in the chicken coop. They were set up with a pedagogical purpose. Let's directly measure and make sure of what, honestly, no one doubts. When an electron flies in the accelerator, first, it moves very fast, and second, it bends its trajectory, and because of this, it emits light, synchrotron radiation. For example, it moves at 0.95 the speed of light and emits light. The speed of the light it emits can be measured. That is, light from a moving source is the same as if it were stationary. It does not push the light. This is not a rocket starting with another rocket. Next, it is important to say, no object can be accelerated to this speed. For example, a cup at rest cannot be accelerated to the speed of light. The energy balance prevents it. And you ask, how is that impossible? Well, you say, you could take a rocket and accelerate it to half the speed of light. That's in principle possible. But if another rocket starts from it, moving at 2/3 the speed of light, would the resulting speed relative to the initial spaceport exceed the speed of light? No. Why? Because other things also work differently. Speeds do not add normally, and the whole scheme turns out to be logically consistent. It contradicts everyday experience because our usual speeds are too small.
The second academician, Kruglyakov, in a direct experiment also measured this effect. The speed of light does not add with the speed of the source for an observer watching from the side. This was a recent experiment, about 10 years ago, as far as I remember, in St. Petersburg, in an optical system with a moving medium, I think water. It was directly proven that arithmetic addition does not work. There is a completely different, strict formula, and it works directly. So there is no doubt. I am surprised that even now there are people who doubt this. I sometimes receive letters from people saying, no, this cannot be. Einstein is wrong. It's all made up.
You know, it seems to me that you gave a great example at the beginning. When you use something and are convinced that, on one hand, you have already made some effort toward abstraction. Newtonian mechanics, after all, is a mathematical thing that requires a certain abstraction from everyday experience. And that experience actually describes very well all our machines, mechanisms, satellites, everything, artillery shell flights, rockets, trips to the moon, planets, well, except for Mercury. And even Mercury, in principle, isn't too bad. And then suddenly it turns out that there is something that contradicts this experience. If you constantly deal with it and it is your way of thinking, you involuntarily continue this way of thinking further. But there is another experience, another experiment. These high speeds are unreachable for our fastest spacecraft. Listen, the speed of the Earth in its orbit is 1/10,000th of the speed of light. In general, the Earth's orbital speed is about 3 times higher than what we can accelerate our spacecraft to. We don't have such speeds.
But nevertheless, it is not a small speed, 30 kilometers per second. And it was precisely the speed that made the Michelson-Morley experiment possible. Whether Einstein knew about it at that time, I don't know.
That's the question, but the experiment was direct. They proved that the speed of light does not depend on the direction of motion through the supposed ether. That is, assuming such a medium exists, you don't know your speed relative to it. But if you measure the speed along the Earth's orbital motion and across it, assuming light moves relative to the ether, then you should get different values for the speed of light. Honestly, they conducted the experiment precisely to try to get different values. And it must be said, this is a good trait of experimenters. They were honest. You know, we really wanted to measure this. Our eyes nearly popped out. But look, with this precision, we stand by it. This, by the way, is another version of the same thing. It should be right at your fingertips, double stars.
Indeed. By measuring the timings of star eclipses, since one moves toward us and another away from us, we can see that they don't push the light. Yes, that's also a good experiment.
This happens constantly in many observatories, more or less daily. But I mean daily, actually every second. All the accelerators in the world, including the Large Hadron Collider and many smaller ones, simply check this whole setup every day, every second, and it raises no doubts. Although in recent years, well, now this urgency has somewhat faded, But about 15 years ago in the solar system, they were searching for violations of Lorentz invariance. This was prompted by the construction of gravity theory, but we don't have a good quantum theory of gravity.
Is there a bad one, gravity theory? None.
None, well said, there is none. General relativity is not quantized. If we did not insist that, in the flat limit where gravity is practically absent, the framework of special relativity, including Lorentz transformations between moving observers, must be exactly reproduced, we would have more freedom in developing a theory of gravity. That is why quite sophisticated experiments were conducted, even on the scale of the solar system, to check for possible deviations.
As far as I remember, these were radio experiments with probes moving away from Earth toward giant planets. Their radio signals were received, and these experiments were conducted by Shapiro.
In general, such searches were done deliberately. They looked for subtle violations of physical laws. But none were found. No physical theory is absolute or eternal. Theories are generalizations of our experimental data, and we use them as long as they work. As with Newtonian mechanics, it worked perfectly until new theories had to be developed, which allowed us to understand the expansion of the universe, black holes, binary black holes, gravitational waves, and so on. We are conservative in sticking to what works, but we also constantly wonder whether we are approaching the limits where these theories will fail. People sometimes write letters suggesting conspiracies in science, but that's not true. Science is a competitive field where everyone strives to make a name through discoveries. Even examples like the Korean researchers claiming extraordinary superconductivity show that science advances precisely where anomalies or inconsistencies appear.
It was not a fraud. It was a misconception or a mistaken interpretation.
I don't know much. It distracts us from the main topic, but there were comments. Overall, it was work at the graduate level. Some things simply weren't measured, for example, where conductivity dropped. An honest mistake, either due to inexperience or a lack of sufficient qualification.
Friends, if you enjoyed our conversation, give us a like.
And if you don't want to lose us, make sure to subscribe too.
And I'll remind you of another story. Scientists tried to directly measure the speed of neutrinos. They were generated somewhere in France and detected at Gran Sasso in Italy, under the Alps. The distance was about 500 to 600 kilometers. The launch and detection times were recorded, and the travel time was measured using GPS and atomic clocks. Initially, it seemed that the neutrinos were traveling slightly faster than light, by about 0.1%. Imagine the shock, it would have shattered all physics. But there was a publication, and the results showed that the neutrinos are traveling faster than light.
This is truly a remarkable story, very relevant. It seemingly challenged what relativity predicts, because neutrinos are hard to detect particles, and there are still many unknowns about them, even their exact mass. The idea that they might exceed the speed of light is extremely strange. In the archives, there were papers where theorists tried to come up with explanations. The experiment was conducted by a highly respected team. Before publication, the team was somewhat divided. Some scientists didn't want to report the results, doubting their accuracy, while others said, "We measured everything, and the experiment shows a speed greater than light, and we must report it honestly." It's similar to the Michelson-Morley experiment. They measured the Earth's motion relative to the ether, but found nothing and reported it honestly. With the neutrinos, however, it was different. The press created a huge stir, there was immense pressure, and theorists immediately began proposing explanations even before official verification. This is a normal reaction in science. Theorists constantly try to explain new observations and compare them with experiments.
Yes, they measured the signal arrival times incorrectly. It turned out that one of the cables was connected improperly, and the antenna receiving the satellite signals had the wrong polarization. One of the technicians had connected the cable incorrectly.
You know, after this, psychologically, confidence in the absence of faster-than-light speeds is strengthened. Even if there were previous doubts, such a check reinforces the belief that the speed of light cannot be exceeded.
And scientists are honest people. They can report what they observe, even if it contradicts common expectations.
Yes. You know, in this whole story, there was an element of a certain mess, an element of noise, and even something harmful. For example, the leader of the experimental group stepped down. Science is not perfect, but it's a mechanism, and this is very important. Everyone makes mistakes, but in this field there is a mechanism for correcting errors. There is self-control due to the competitive environment. Everyone is constantly watching each other. The story is instructive. It contains all elements: honesty, error, and an element of noise.
And small conspiracies among scientists also happen. They don't want to make noise at first and prefer to check their results. For example, FVO made a discovery in the fall, but announced it only at the beginning of 2016, keeping it quiet and secret.
Listen, I have a friend, and we talked, including about waves. He didn't really show anything specific, but his story made an impression on me, even when I later revisited it.
It's a kind of conspiracy, but not to hide anything, just to avoid mistakes and present a reliable result. Am I correct?
Yes, because you need to avoid messing up to verify results. It's part of one's reputation. Look, I'll repeat again. Science isn't an ivory tower. It's the same living people, but there are mechanisms that, in some other fields, are less pronounced, which uphold moral standards and quality. Special relativity. Now let's consider the general case. General relativity isn't exactly the same. The idea is how to transform observations from one observer to another when there is gravity or fast motion. It's like accelerated motion, which in a sense simulates gravity, or perhaps doesn't simulate it at all, but is simply its full analog.
Okay, let's discuss the most famous thought experiment called the twin paradox. What is it about? We can illustrate who stays and who moves and in which situation. Which twin ages more and which less. This paradox was demonstrated clearly. An older and a younger one, although they were twins. The thought experiment needs to be properly organized on Earth.
All right, first I'll organize the experiment the way it's convenient for me. Since you gave me freedom, let's assume there's a spaceport on Earth. Why immediately on orbit? From the spaceport, a rocket launches. It moves along a geodesic, which doesn't mean no forces act on it, but it flies under the influence of gravity alone. The rocket starts from there. All right, we'll send you.
We are twins. Yes, let's assume we look the same in general, and overall similar.
I got into the rocket, said goodbye to you, hit the gas, and accelerated. You can keep accelerating, and it is claimed that your time flows differently than mine.
How can this be tested?
We can exchange radio signals. I will see that signals from you arrive, noticing that time on your ship passes more slowly than mine. You, in turn, will see that on the spaceport time passes more slowly than on your ship. It seems paradoxical, but there is no actual paradox. We are simply two different observers. The distance increases and the signal takes time. If we place a huge magnifying glass between us, as in Martin Gardner's example, I will see you smaller than me, and you will see me smaller. And there is no paradox here. If you travel in space and then decide to return, you turn on the engine, stop, or slow down. In space, braking is the same as accelerating. You need enough fuel, or you will be in trouble. When we meet again, our clocks are synchronized from the moment of departure. But on your board, 5 years may have passed, while I on Earth have aged 15. In films illustrating this, you see your daughter as an old woman or other people, and civilizations may no longer exist. Building such a rocket is actually impossible. But the idea of the twin paradox is that time for two twins moving along different paths turns out to be different.
What exactly was the difference between us?
The difference between us was in our frames of reference. While you were passing by me, for example like the asteroid Oumuamua, imagine tiny beings on it sending me radio signals according to a prearranged agreement. I see that their time relative to me flows slower, and they see that my time relative to them flows slightly slower. This is the principle of relativity and the equality of observers in special relativity. However, when you traveled and returned, you experienced accelerations and decelerations, changing your frame of reference. The crucial point is what happened at the moment we met, when you arrived, and our clocks were compared. Different ways of describing this give slightly different explanations, and that is normal. One can consider that time dilation occurred while you were firing the engine, and under the effects of acceleration, pressed against the floor or the seat of your spacecraft. Einstein, when developing general relativity, considered one of the happiest thoughts of his life to be that acceleration and gravity are not just similar phenomena. They are the same. Because of acceleration and the work of your engines, time for you passed more slowly.
Because you experienced high gravity due to acceleration. The rest can be modified in the experiment. And this is what I don't fully understand. Imagine that one twin doesn't float in vacuum, but stays on Earth under the influence of gravity of 1g.
Yes, but it's affected not only by Earth's gravity. What else? Right, it's also supported by the ground.
Support? Yes, I agree. This could also create a difference. One twin stays on Earth, while the other travels in a rocket with constant acceleration of 1.
Very comfortable. By the way, you have Earth-like conditions there.
You are flying in one direction, and then, halfway, he turns the engine the other way. In a second, slowing down. Then he continues flying under constant acceleration, the same as his twin on Earth.
Einstein noticed that under acceleration, like in an airplane, all objects, light and heavy, move with the same acceleration. This is not about heavy objects standing on the floor being held by friction. If everything is smooth, they move with equal acceleration, as if the plane falls away from under them. Similarly, in a gravitational field, a brick and a feather fall with the same acceleration, independent of their mass. Galileo understood this using thought experiments, even without the ability to remove air or perform precise experiments.
It would be interesting to show him the direct vacuum experiment with a hammer and a feather on the moon during the Apollo 15 mission. There, they fell at the same rate.
By the way, Shepard was an American hero, the first American in space. He performed a suborbital flight, which, from Yuri Gagarin's perspective, was insignificant. Americans were proud of him, and he became a millionaire by leveraging his fame. Later, he was temporarily removed from flights, then returned after an ear operation. On the moon, he took a golf club, placed a ball, and hit it. Interestingly, in lunar gravity, the ball is attracted with only 1/6 of the force it experiences on Earth, but its inertial mass remains the same. Therefore, it will not travel faster horizontally and will fall more slowly if thrown upward. How well he managed this in a spacesuit with gloves is difficult to judge. In such gear, it's hard to hit the ball precisely, and only the hit is visible on camera. The principle is clear. A hit with a golf club applies a constant force, accelerating the ball to a certain speed. If the ball is twice as heavy, the same hit will give it half the acceleration. Gravity works differently. A more massive object receives proportionally the same greater acceleration. Einstein noted that this might seem like different phenomena, but in fact, they are the same, a manifestation of a general law of nature. Objects move in three-dimensional space, and in four-dimensional space, their motion follows geodesic lines.
Interestingly, this did not surprise Newton. He recognized that there is a small letter m used in the school formula for gravitational force. The same principle applies to the second object as well.
This did not surprise Newton. He tried to test experimentally whether inertial mass and gravitational mass are equal. I recall the details vaguely, but the accuracy at that time was about 1%, not very precise. Later, this law was tested more accurately, and eventually famous experiments were conducted by other scientists, including Brzezinski. This shows the subtle tuning of nature. The response for inertia and the gravitational charge of a body is carried out in exactly the same way. By the way, alternative theories of gravity, which are periodically discussed, are constantly tested against the equivalence principle. This principle asserts the exact equality of gravitational and inertial mass. Experiments measure whether these two masses truly coincide with high precision. If there were a theory of gravity that violates this principle, we would have to operate at the very limits of modern instruments' precision to detect any deviation. In practice, people occasionally repeat these measurements to try to find any possible differences. Alternative theories of gravity do exist. They introduce additional parameters or fields to general relativity. It turns out that general relativity describes a single field with 10 components, which determine how spacetime is curved at every point. That is, how distances defined by the Pythagorean theorem are modified in four-dimensional spacetime.
Is this what is called geometry?
Yes, it is geometry. The Pythagorean theorem allows us to measure distances. I know the distance along one dimension, another, and a third, sum their squares, and get the square of the distance to, for example, a fly on the ceiling. You could, of course, use a ruler, but if that's impossible, you measure along each direction, and use a three-dimensional or four-dimensional, including time, scheme. In relativity, these calculations require corrections that depend on the point in space-time and the masses of objects. These corrections represent gravity. They modify the plane of the Pythagorean theorem, creating curved space-time. General relativity describes this minimally, but one can add other fields that slightly push or pull objects differently. Such modifications are real, and there are many such theories. Some introduce a second field for a different effect. Some scalar theories add extra fields. In general, Riemannian geometry, used in general relativity, can be extended by these additional fields. The minimalist version is Einstein's general relativity. It is interesting to test how well it works and where its limits lie.
Which objects could help in this context? Black holes. Well, neutron stars?
Neutron stars. Even neutron stars already suggest black hole event horizons. Let's start with Sagittarius A, a star 26,000 light-years away in the center of our galaxy. Is this related to the Nobel Prize? Not entirely without reason. The prize mentions a compact object, essentially a void around which stars orbit. If stars move around a void, it attracts them. No light comes from it, so we assume it's a black hole. We observe the fastest of these stars. Its orbital shifts are so large that in 20 years of observation it has completed more than a full orbit.
Then there is S2, a well-known star. It has a small orbit and completes a rotation roughly every 10-15 years.
We have already tracked its movement. It rotates apparently about 4 degrees per year, so it spins noticeably. This is exactly the effect Einstein identified for Mercury, and he was thrilled. We apply the same principles. From the orbits of these stars, we estimate the mass of the black hole. More complex reasoning follows, regarding whether the black hole itself is rotating. I don't know the details, but such calculations are also done. Then this knowledge is used to determine what precession the orbit should exhibit at a given distance, using the Mercury effect. Observations show that the orbit indeed exhibits this effect, although the precision is not extreme. Nevertheless, it's reassuring. If the orbit behaved differently, we would know something was off, and we constantly think about where Einstein might be wrong.
So he's not a saint, he's a physicist?
We consider general relativity as the best theory of gravity so far. First, it is not quantized. We'll discuss this later. Even if experiments show it needs to be replaced, it will remain an important milestone because it introduced a whole class of theories and demonstrated how they work. It has a wide range of applicability. Newtonian mechanics and gravity work excellently in the solar system, except for Mercury. And we still use them. They apply to the entire universe.
Not just Mercury, I remind you. Relativistic celestial mechanics helped launch probes to Saturn. To fly between the inner edge of its rings and the planet's surface, relativistic effects had to be taken into account. We have a specialist, Brumberg, who authored a monograph on relativistic celestial mechanics and participated in these calculations, along with other experts. So even within the solar system, when precise targeting is required, calculations according to Einstein are necessary.
Yes. General relativity works as long as objects are large. It also explains the expansion of the universe and that time slows down. When I approach a black hole and you watch me fall toward the event horizon, you see that time for me slows down more and more. You will get tired of watching, go have some tea, and later maybe retire and write a book about it, while from your perspective I still never reach the horizon.
Physicists have a saying, now you can watch endlessly how water flows, how fire burns, and how someone falls into a black hole.
Literally, this can be observed endlessly. Whereas if you throw me into a supermassive black hole, I hope I'll have at most 1 day left.
And nothing terrible will happen to you, except for the very last millimeters near the event horizon. You will continue falling, and I will never see it. It's good that I stayed outside.
Think about this. Staying outside, you'll have time to wonder whom I might meet there, but I'll never tell you. I won't have a reference frame to observe from, because as you said at the beginning, gravity is extremely strong. Our world is fundamentally quantum, so quantum effects must be considered when gravity is extremely strong. General relativity is a limited classical theory. Despite enormous efforts, we don't know how to make it quantum. Sometimes it's even thought that maybe it isn't necessary and something else occurs. However, it breaks down near the center of a black hole. The equations indicate that mass is concentrated at a single point. In reality, time there ends, it doesn't just stop. This is called a singularity. It's not a physical phenomenon, but our ignorance of what actually happens there.
Tell me, is it possible for gravity to become comparable to other physical forces? Electromagnetic or nuclear? It should always be weaker. Right now, we're sitting here, each about 70 kilos, a meter apart. The gravitational pull is so weak that we don't feel it. Physically, our chemical bonds dominate. I even recently calculated, the force with which we are attracting each other.
About 1/1,000,000th of our weight, probably.
In normal, everyday units, that's about 1/100th of a milligram. Right now, the mutual gravitational force between us is barely noticeable. Of course, we feel gravity with Earth because it's massive. But why, in some situations, should gravity become comparable to other strong physical forces?
In the Standard Model, which describes interactions between elementary particles, gravity doesn't participate at all. It plays no role. When does it start to matter? First, we expect certain effects from quantum gravity. It becomes relevant when the equations of general relativity go crazy, producing infinite density, infinite curvature, and so on. This means the theory needs to be replaced or supplemented, considering the quantum nature of the world. Under such conditions, the concentration of matter becomes so extreme that even weak gravity becomes significant, but the density must be absolutely enormous.
So, is it impossible to perform such an experiment?
Such an experiment is impossible. Everything goes beyond limits. You lose the ability to measure, because this is the boundary of general relativity. The theory begins to fail. At extremely small scales with high matter concentration, the volume turns into a tiny black hole, and you cannot observe or measure anything. This is crucial in physics. You lose the fundamental ability to say what's happening. Galileo could bring a ruler and measure, but here no ruler can fit or be extracted. The structure of space-time collapses at extremely small scales with extreme matter density. Perhaps this happened before the Big Bang, the hot phase when the observable universe had a volume and general relativity worked perfectly, retaining traces of quantum fluctuations. But what happened before that, inflation and its origin, should be explained by quantum gravity, which we may never know, because there is no experimental data and no way to obtain it. Nature seems to be against us. Look, this is why astrophysical black holes are so interesting. At the center, where the singularity is, general relativity breaks down in a certain way. Something happens there that we don't know. Could what happens inside somehow manifest outside the event horizon? We don't know what effects might be visible from the other side of the horizon. This is extremely fascinating. It would be great to have several black holes of different sizes in the solar system for experiments, so that by throwing objects in and observing other effects, we could finally understand what happens.
For ecologists, that would be a real find. All waste could be sent there.
In general, black holes are colossal guardians of the universe's entropy, concentrators of entropy. What role they play in the overall evolution of the cosmos? Perhaps some role. They collect fundamental waste, processing matter to a state where no details remain. Entropy represents lost information. We cannot track where each molecule or elementary particle goes. Charge is conserved, but nothing else. Quantum effects are important here, although a consistent theory of quantum gravity does not exist. By combining principles of quantum mechanics and general relativity, Hawking extended Bekenstein's ideas about black hole entropy. At first, he thought the ideas were wrong, but starting his paper, he realized black holes do have entropy. That is, they have a temperature for an external observer and emit thermal radiation. Any body, even if not very hot, has a temperature and emits radiation, because in the quantum world, temperature is linked to particle motion. General relativity cannot answer questions about black hole entropy. This is its boundary. The radiation is weak for large black holes and negligible against the cosmic microwave background. Only very small black holes emit strongly and rapidly, flashing Hawking radiation. You would need to somehow create a factory for producing tiny black holes to detect Hawking radiation. One could look for indirect traces or analyze the spectrum. It's a very interesting question. Our mutual friend Sergei Popov believes that within 5 years it might somehow be detected, though exactly how is unclear.
But you know, the most interesting place where this formula for black hole temperature was published is not on paper.
I know that on Schrödinger's grave, the Schrödinger equation is inscribed. A special place. On Boltzmann's grave, it wasn't Boltzmann himself who wrote the formula, but Planck, who created it. And later someone arranged to have Sklag W inscribed on Boltzmann's grave. And instead of a photo of the person, as is usual on graves, there is nothing.
On Hawking's grave, the formula is also inscribed. The inscription reads, "Here lies the body of the mortal Stephen Hawking," while the formula inside represents what remains immortal. It will likely be impossible to confirm it experimentally.
I'm not a specialist, but this seems like a problem several orders of magnitude more difficult than the most complex ones we can currently handle.
Could tiny black holes be created, for example, in an accelerator by colliding protons?
No, this has been discussed. The density is insufficient. To create a tiny black hole, matter would have to be compressed to an incredible density, but it doesn't work that way. General relativity, combined with other principles, essentially blocks us from doing this. It says, if you try, your objects will become black holes. There are also indirect indications. Strangely, general relativity combined with calculations of entropy and temperature shows that the capacity of a black hole should be measured not by volume but by the area of its horizon. Normally, we measure the capacity of a trunk or backpack by volume, but here, the amount of matter you can put into a black hole is determined by the horizon's surface area.
Because it's easy to convert the area of a sphere into its volume.
No, it's not just about the radius. There's no universal conversion between square centimeters and cubic centimeters. This is surprising, but it's because objects inside a volume interact gravitationally. Gravity doesn't allow you to pack in too much matter. Once a black hole forms, its content is measured by the surface area. This implies that our entire world governed by gravity might be described by information encoded on its surface. Imagine an imaginary surface far away. You could place information about everything happening inside that region of the universe on it. This is called the holographic principle. If confirmed, it would indirectly support these ideas. General relativity, before it loses applicability, says one last thing. You cannot measure the capacity of an object by its volume. It's measured by the surface area.
Is this still within the framework of general relativity?
This is the last thing it is able to tell you.
It would be interesting to see, at least in the near future, a theory that surpasses general relativity. But for this, experiments and astronomical observations are needed, because a physicist in a laboratory is unlikely to test or prove its failure in certain situations. Astronomy has already reached scales of energy, distances and sizes where some shortcomings of general relativity might become apparent.
For gravitational astronomers, the current picture is this. Gravitational waves confirm the equations of general relativity. They create a library of expected signals from black hole and neutron star mergers, considering masses and impact parameters. When a signal is detected, it is compared to the library, identifying, for example, a black hole of 1518 solar masses merging with a neutron star of 2 to 5 solar masses. Researchers carefully look for strange effects, like echoes, from the black hole's horizon. The horizon isn't a solid object, and general relativity says that crossing it you would feel nothing. But if the theory is not perfect, small corrections might appear at the horizon level. So far, there is no clear independent confirmation of this.
The first steps of gravitational wave astronomy are still in their infancy.
We aim to detect gravitational waves that survived from events predating the hot Big Bang. These remnants could lead us to the next level of hypotheses. There is no alternative. Experiments cannot be carried out not only on Earth, but anywhere in the solar system. We lack the resources and even the fundamental possibility to do so. Therefore, we must carefully listen to the universe itself, as it whispers traces of what it was like in those early times. By attentively catching this faint cosmic whisper, we may gain new insights.
3 satellites will measure the distances between each other. When a gravitational wave passes, they will slightly tremble, and we will be able to detect it. Hopefully, in the near future, this project will provide us with new insights.
None of our theories is a dogma, and nature constantly reminds us of this. This does not diminish Einstein in any way. On the contrary, the steps he made became the foundation for future discoveries, just as Einstein never diminished Newton, and certainly not Galileo.